Our next speaker is Xiangyu Gao. He is a fourth-year PhD student in the NYU Computer Science Department. His research interests are in computer networks and programming languages with a focus on synthesis and compiler design for applications in programmable switches. Okay, Xiangyu, take it away.
Hello. Yeah, so thanks for the introduction. I'm Xiangyu from NYU. Today I will present our work, CaT, a solver-added compiler for packet processing pipelines. So this is joint work with collaborators from NYU, Princeton, and Rutgers. So traditionally, network devices have limited programmabilities, and now, motivated by growing and complex demand, in modern-day computer network, people want more functionalities and complexities. For example, they want to implement firewall, network monitoring, and load balancing to these devices. Therefore, programmable network devices have become more and more popular. Typical devices include Belfort Tofino switch, Xilinx LVO FPGA, and SmartNIC. And P4 has become one of the widely used language to program into these hardware devices. So it is easy to get started with writing P4 programs. For example, you can read the tutorial or you can attend a workshop. But writing programs that can run on programmable switch is quite hard, mainly because of the reason that the hardware constraints in the RMT pipeline switches is very demanding. So what is RMT? RMT is short for reconfigurable match table. So this was proposed in CCOM 2013. In this figure, we can see that PHP containers will be used to store the network packet fields. Stateless ARU can modify the network packet fields, and the stateful ARU can modify both persistent switch state and packet fields. Input marks will determine the input of each ARU, and output marks will decide which variable will be passed to the next stage. The structure is similar across stages. So state-of-the-art efforts have been made to deal with this challenge. For example, people will develop compilers, but existing P4 compiler have multiple limitations in terms of compilation speed and compilation quality. And people also want to design the new domain-specific languages, but this newly developed language still rely on the P4 compiler. Let's take a look at this challenge and state-of-the-art effort in more detail. First is about the challenge. Basically, for example, the switch hardware is really resource constrained. I mean, the RMT pipeline gives us a lot of flexibilities in terms of guarantee of the line rate throughput at the cost of less expressive ARU, and they only support feeding packet forward. So in addition, the network hardware, like the programmable switch, is all or nothing fit. Basically, a program can either fit into the hardware and run at the full line rate, or the compilation fails. There's no mid ground in between. As a result, we think compiling and optimizing P4 programs are important and demanding tasks. So the first previous work is to develop P4 compilers to make the whole process automatic. But existing compilers have multiple limitations. For example, Chipmunk compiler suffers from slow compilation speed. Tofino compilers, this is a commercial compiler, has no support for transactions in P4. And both Domino compiler and Tofino compiler will support or lead to suboptimal resource usage. So in practice, based on the feedback from a lot of industry people, a lot of manual work is necessary to make the compilation process successful. And some compilers do provide techniques for fitting, but may miss some solutions. And the second effort will be related to design new domain-specific language, including Lyra, Lucid, P4, and the Citus. So they do provide some freedom for the programmer to write the program easily, but they will turn to P4 program before running in the programmable switch. Therefore, any improvement to the P4 compiler will be complementary to their contribution. So therefore, we know the problem will be we want to compile complex P4 program into programmable network devices efficiently by designing good compiler. So what do we mean by good compiler? There are some metrics of good compiler. The compiler should be fast, should generate high quality compilation result, should support expressive P4 programs, and also be consistent over all the outcomes. Therefore, we developed a compiler called CaT. This is a new P4 compiler that leverages solver-added technologies to compile P4 programs. So in general, our CaT leveraged the high-level synthesis idea to decompose them into three stages. Three phases. The first phase is resource transformation phase, and second one is resource synthesis, and third one is resource allocation. And we also make our compiler retargetable. In our experiment, we retarget at Tofino switch and motion cycle accurate simulator, depending on the hardware architecture and the ARU's functionality. So why we need to do this decomposition? Because we want to strike a trade-off between the computation speed and the computation quality. Basically, Chipmunk regards the computation problem as one program synthesis problem at the cost of long computation time, but achieve optimal result. Domino can generate the result pretty quick, but at the cost of suboptimal resource usage. And in addition, there is some synergy effect between phases. For example, resource transformation phase can reduce the number of resource allocation constraints. And the efficient resource synthesis can use fewer pipeline stages, which loosen the constraints for the resource synthesis. Let's go to each of the phases in more detail. The first phase is called resource transformation. In this phase, we will automatically rewrite a program into another semantically equivalent version, which consumes fewer resources. Basically, we will perform guarded data dependency analysis to identify force dependencies and turn the ITE statement into match action tables. Let's take a look at a simple example. So now we can see these two statements, P2 equal to P2 plus 1, P2 equal to P2 plus 2. They may have right after right dependencies. However, if we take the path information into consideration, and we can see that at most, one of the if predicate will be true because V1 is not equal to V2. Therefore, we can transform it into another formula by adding this key value else. And finally, we will turn this ITE statement into a match action table so that in this scenario, we only need to use one stage and without any use of scarce resources such as gateway. So after resource transform, we can find that CaT compiler saves the pipeline stages of all three motivating examples extracted from real cases written by other academic users. In this scenario, we can see like after transformation, they save the number of gateways, they save the number of tables, and they save the number of pipeline stages usage. The second phase is to do the resource synthesis for a particular actions in the P4 program locally. Basically, we want to generate high quality code for multi-action stages, multi-stage actions and stateful transactions in P4 programs with simpler synthesis queries and optimal synthesis result within a query. And in order to achieve optimality, we also designed some other optimization tools such as folding and predecessor packing and staged input tree grammar. So please refer to our paper for more details, but I will spend a little bit more time to describe what we mean by min-depth tree synthesis. So suppose we have the program statement is E equal to A plus B plus C plus D. The default expressing tree requires 3 stages, but we can easily find another solution which only use 2 stages. So in our program synthesis phase, we can use program synthesis tools to find the min-depth expressing tree by considering all possible solutions within a particular depth. And the synthesis specification is the program update, and the ARU will capture the grammar. So in terms of the result, I have to note that this phase takes up most of the time of the compilation. Therefore, we want to compare it against Chipmunk and Domino because both of them use program synthesis to do the code generation. So against Chipmunk, we can see that CaT can generate faster code in like 19 out of 24 benchmarks. And on average, the speed up is 3.5 times and the maximum speed up is 50 times. And in terms of the resource usage, Chipmunk can have the same performance as CaT to 23 out of 24 benchmark. And CaT only use 1 extra stages for 1 benchmark. Against Domino, CaT successfully compiles all programs, but Domino fails to compile most of them. Actually, Domino fails to compile 18 out of 24 benchmark. So finally, we will go to the third phase is to do the resource allocation globally. In this phase, we will schedule each type of resources into the hardware pipeline stages. And we formulate as an integer linear programming problem and leverage SMT solvers such as Z3 or IRP solvers such as Groby to find either a feasible solution or an optimal solution. The users can choose whatever they want depending on their preference. But in our experiment results show that Groby solver with an optimal mode might be a good default. To conclude, we developed a compiler called CaT, short for code generation and table allocation, that consists of 3 phases. And experiment results show that it can quickly generate code with close to optimal resource usage. In the future, we also want to transplant this compiler to handle other network substrates such as SmartNIC, eBPF, and DPDK framework. Thanks for your listening, and I'm happy to take any questions.